In order to discuss acids and bases, first we must go over what strong acids and weak acids are. Here is a list of strong acids and bases. Now, here is a list of weak acids and weak bases. As we examine the differences between weak acids and strong acids, we see that one completely dissociates. The single arrow shows that the strong acid and the strong base completely dissociate, while the reversible arrow shows that the weak acid and the weak base are reversible. So what does it mean to be reversible? Reversible reactions like weak acids and weak bases means that the products can form from the reactants and the reactants can form from the products. In the next part of this video, you will see how strong acids, strong bases, weak acids, and weak bases differ in their mode of calculating the pH. pH is a measure of the negative log of the hydrogen ion concentration. This is important to determine the acidity and alkalinity of anything in a solution. Just for reference, strong acids tend to have very low pHs between 0 and 2. Strong bases tend to have pHs around 13 to 14. Weak acids have pHs greater than 2, and weak bases have pHs lower than 13. 7 is neutral.
So the first question is to calculate the pH of a 100 milliliter solution of 1 molar sodium hydroxide. So to do this, we first want to write out the equation, as we should always do with any problem. So we'll say NaOH dissociates into Na plus ions and hydroxide ions. So in this situation, all we're really concerned about are these hydroxide ions, of course, since that's what determines the pH. Since it's a strong base, we know that this sodium hydroxide here completely dissociates into these two components. So what we can say is this 1 molar solution of sodium hydroxide turns into a 1 molar solution of sodium ions and of hydroxide ions. So we can say that the concentration of OH minus ions at equilibrium is equal to 1 molar. Now that we know the concentration of hydroxide ions, what we can do is say the POH, right, is equal to the negative log of the concentration of hydroxide ions, which we know is 1. So we can say the POH is equal to the negative log of 1. Okay. So now you have to think a little bit. What is the log of 1? Well, the log of 1 would just be 0. So we're saying the POH is negative 0. So the POH is just 0. Now we have the POH. We're not quite done with the question because we were asked, if you recall, what is the pH of the solution? So for this, we need to realize that the POH plus the pH will always be equal to 14. So now if we substitute the value of this POH into this little equation here, we end up getting 0 plus the pH equals 14, and thus the pH is 14. So summarize, the pH of the solution is 14, which is very basic, as one would expect from a strong base solution. So the next question we have is to calculate the pH of a 50 milliliter solution of 1 molar hydrochloric acid. So for this question, we'll be treating it similarly to the sodium hydroxide question, but this time what we'll be doing is dealing with pHs rather than POHs, and because of that, we won't have to deal with that second step in the sodium hydroxide question, where we had to say the pH plus the POH equals 14. So what we're going to start off with is the equation, as always. So we'll say HCl dissociates into H plus ions, and of course chloride ions. So again, what we're interested in here are the H plus ions, because that's what determines the pH of a solution. So what we should know going into this problem is that hydrochloric acid is a strong acid, meaning that it completely dissociates in solution, right? Completely dissociates. And because of this, what we can say is that since the concentration of HCl was 1 molar, we can then say that, therefore, the concentration of H plus will also be equal to 1 molar. So now what we do is we substitute things into the pH equation. Since pH is the negative log of the concentration of H plus ions, we can say that the pH is equal to the negative log of 1. And again, the log of 1 is 0, so this evaluates to 0. And that is the answer. The pH of the solution is 0. As you may notice, this value for the quantity of solution is irrelevant in these kinds of problems, since it really doesn't matter how much of the solution we're dealing with here. So the next problem we're going to do is calculating the pH of 100 milliliter solution of 1 molar acetic acid. So unlike the strong acid and base problems that will be done, this weak acid problem involves what we call a Rice table. So a Rice table is essentially a representation of what takes place during this shift towards equilibrium. So the R stands for the reaction, and so what we're going to do is we're going to write the reaction out right next to the letter R. So we know acetic acid. In this case, I'm just going to use H, and I'm going to use this representation of the acetate ion. I'm going to write ACET. So just for reference, ACET equals the acetate ion. So what I'm going to do is I'm going to write out H acetate as a representation for acetic acid. And I will say that dissociates to H plus, and of course, the acetate minus ion. So now the I part stands for the initial concentrations of each component. And as you see above here, we're given that it's 1.0 molar acetic acid. So we can simply fill in 1.0 molar for acetic acid. And the other two will be given values of 0, since there is none existing in solution prior to this shift in equilibrium. So C stands for change, and so that's what takes place as equilibrium is approached. So for every molecule of acetic acid that reacts, one atom of H plus and one molecule of the acetate ion will form. So we can represent this in terms of X by saying negative X for acetic acid is the change, and positive X is the change for both H plus and acetate minus. Equilibrium is simply the final product in terms of concentration. So let's take acetic acid for example. It starts off with 1.0 molar, and we then subtract a negative. We add negative x, so we subtract x. The result of that is 1.0 minus x. Likewise for H plus and acetate minus, the results are x and x. So now what we do is we take these values that we've gotten in terms of x, and we substitute them into what we call the Ka expression. So the Ka expression for any weak acid or base will be the concentration of the products multiplied by one another divided by the concentration of the reactant. So in this case for acetic acid, it will look something like this, with the concentration of H plus on the top, along with the concentration of acetate minus, all divided by the concentration of acetic acid. So what we can do is start substituting in values. And if you see above here, the Ka is given to us, and we can simply add that to this down here, is equal to x times x divided by 1.0 minus x. So we can multiply these two x's with one another very simply, right, by saying 1.8 times 10 to the negative fifth equals x squared over 1.0 minus x. The question comes up though, what do we do with this 1.0 minus x term? Well, what we do is something called small x approximation. So what we know is that the value of x in this situation over here, the value of x is going to be relatively small compared to the value 1, right? We know x is significantly smaller than the value 1. We just know this. And because of this, what we can say is that this value here, this 1.0 minus x term is going to be very, very, very close to 1.0. And so what we can do is simply just ignore the x. So this expression turns out to be 1.8 times 10 to the negative fifth equals x squared over 1, which is simply x squared. So now we take the square root of 1.8 times 10 to the negative fifth, right? And that'll give us x, which is the concentration of H plus in solution. As you see above, x is the, as you see here, x is the concentration of H plus at equilibrium. So after we solve for x with the calculator, we end up with the following, 0.0424. So now to find the pH, we take the negative log of the concentration of H plus, and that would be negative log of 0.00424, which in turn equals, let's see, that'll equal 2.37. So the pH of the solution is 2.37.
The procedure for solving weak acid problems is exactly the same as procedure for solving weak base problems. The only difference is H plus will be found for weak acid versus OH minus, which will be found for weak base. In order to convert, use a conversion factor, pH plus POH equals 14. Although the scope of the video is limited to acids and bases in terms of general information and calculations, there are further applications of acids and bases in terms of buffers and titrations. Buffers are solutions that are resistant to changes in pH, and titrations are important to determining pH. Now, just to recap, acids are generally low pHs. Bases are generally high pHs. The procedure for strong acids and strong bases for calculation purposes of pH is generally the same. The calculation of weak acids and weak bases is also generally the same. The only difference is the conversion factor POH plus pH equals 14.